Good morning, students. In this class, I am going to explain about the inverse Z transform. This is the topic of inverse Z transform. That unit 5 is completed. So that we have to go for the remaining part, leftover part in the 4th unit. So now, I am going to discuss about some of the problems in the inverse Z transform. Anyway, in the previous classes, we have studied how to obtain the Z transform of a given signal. As we know, Z transform is a powerful mathematical tool which is used to analyze the discrete time signal such as x of n. X of n, it is a discrete time signal. It can be analyzed by making use of the Z transform, so that Z transform will convert the discrete time signal into the Z domain signal that we can call it is x of z. So this we have discussed in the previous classes. So if in the case if we have x of z, then we should know what x of n is. What x of n is. In that case, we have to apply the inverse Z transform. Inverse Z transform. That means the given signal, it is in the Z domain, but we wanted to know it is a discrete time signal. So we wanted to know the same signal in a discrete time in its nature, so that we have to calculate what is x of n is. In the previous class, I have explained that x of n, it is a discrete time signal on which we will be applying the Z transform, so that we can get the x of z. If x of z is a Z domain signal on which we will be applying the inverse Z transform, so that we can get the x of n. This pair is called as a Z transform pair that can be represented as x of n on which we applied the Z transform, so that we can get the x of z. X of z on which we will be applying the inverse Z transform. Inverse Z transform is nothing but it is one of the part in the Z transform only, so that we can keep that is Z transform. X of z on which we will be applying the Z transform, so that we can get x of n. This representation of Z transform is called as Z transform pair. Z transform pair it is called. Now we have to go with the one of the problem in which we have to see the determination of inverse Z transform such that we should know what is x of n is. Now I am going with the one particular problem. That problem is x of z we have. X of z we have, that is 1 by z minus a. But we have to know what is x of n is. X of n is nothing but what? It is the discrete time signal. So we have what? We have x of z is equals to, we have it is 1 by z minus a. I can write this was 1 by, if I take z is common here, this is about 1 minus a into the z to the power of minus 1. I can write this one. So now I can expand this one is I can write this one z to the power of minus 1 into 1 minus a z to the power of minus 1 whole power of minus 1 we can write. So by having the Taylor expansion, we can write this is about, see this one here, I can write this one by substituting the various values. I can write here, substitute, multiply this one, this is about the z inverse. I can write and this is equals to, from the Taylor's expansion, this is equals to, we can write it is 1 plus a into z to the power of minus 1 plus a square into z to the power of minus 2 and so on. This is the Taylor's series expansion. So now I can write this one is, then multiply with the z inverse, so that I can have this is z inverse plus, I can write this is a into z to the power of minus 2 plus a square into z to the power of minus 3. We are multiplying with the z to the power of minus 1 and so on. So if you write this is in the form of a sigma, I can write this is, so now this term is at a minus 1 onwards is there, so that I can write n is equals to 1, I can keep n is equals to 1 and n is equals to 1, and here it is going with the up to the infinite, so that I can write sigma n is equals to 1 to infinity. And here a term, you can assume that here a term is 0. Now I can see this a term is 0. Here a term is 0, that is a power 0, and this is a power of 1, this is a power of 2. This is associated with a power of 0 is associated with the z power of minus 1 plus a power of 1 is associated with the z power of minus 2. That means what? There is a variation of 1 here. Here 1, here 1, here 1. So that according to that one, we should write that one. I can write this is, if this is z to the power of n, z to the power of minus n, because we need to have the standard formula in the form of z to the power of minus n. Now I can write this is, I am writing this is z to the power of minus n, z to the power of minus n, n is nothing but from 1 onwards, so that it is satisfying this equation. But here it is a to the power of n minus 1, it has to be 0, so that n we are assuming 1, so that n minus 1 you can write. So that, see this one now, sigma n is equals to 1 to infinity a into u power of a to the power of n minus 1 into the z to the power of minus n. This is the standard form of the the standard transform of the z transform. So standard formula z transform, I can write this is in another form also. See that one. So here we can write this equation as sigma n is equals to 1 to infinity, that is clear, and a to the power of n minus 1, and at n is equals to 1 onward, at n is equals to 1 onwards only we are calculating, so that you can write that is unit step signal is u of n minus 1, we can write into z to the power of minus n. So that means what? Here this total part is this total part, we can call it is x of n, we can call, and into this is z to the power of minus n, sigma x of n into z to the power of minus n. That is nothing but it is the standard form of z transform only, standard form of z transform of x of n. We know that the x of z is equals to, x of z is equals to, we know sigma n is equals to 0 to infinity x of n into z to the power of minus n. So that means what? Here we have the x of n on which we applied the z transform, such that we got the x of z. But now in place of x of z we have this in which we applied the inverse z transform, so that we can get this is x of n. X of n, that means what? Here whatever the part is there, that is nothing but it is x of n only. Now this is x of n. One can ask the doubt, u of n minus, why we are keeping u of n minus 1? U of n minus 1, if you take u of n is equals to 1 for n greater than or is equals to 0, 0 for n less than 0. That means what? Here we are having u of n, that is amplitude is 1 for n is greater than or is equals to 0. But u of n minus 1 is equals to 1 for n is greater than or is equals to 0. For n is greater than or is equals to not 0 now, here 1. From n is greater than or equals to 1, that will be 1. So that this term will be 1, only 1 into a to the power of n minus 1 into z to the power of minus 1. So that what we got now, x of n, we got x of n, we got here x of n is equals to this part we got is equals to a to the power of n minus 1 into u of n minus 1. This is the x of n. If we apply the z transform on this one, you will get the z domain signal, that is x of z is equals to 1 by z minus a. This is about the solving the problems in the inverse z transform. Then I am going to explain the one more problem such that everything will be clear now. So one more problem, that is what, x of z we have, x of z we have, that is x of z is equals to 3 by z minus 2, and from that we have to calculate what is x of n is. That means if we have the x of n, we can convert that is into the x of z by making use of the z transform. If we have the x of z, we can get the x of n by applying the inverse z transform. So in short, we can call it is z transform, and the inverse z transform is also, it is the counterpart of the Laplace transform. And now we can write this is x of z is applied in on x of z, we are applying the inverse z transform such that we can get x of n. Now take the x of z, what we have, x of z is equals to 3 by z minus 2. So as similar to the previous case, 3 by, take the z is common here, so that if I take the z is common, 1 minus 2 into z power of minus 1 I can write. 3 by z into 1 minus 2 z to the power of minus 1. So that what we can write here, 3 as it is, I am taking the z is to the numerator, so that z power of minus 1, and here I can write it is 1 minus 2 z power of minus 1, and it is also numerator. So by applying the Taylor series expansion, you can write this is about the 3 and z power of minus 1, very similar to the previous case only, that is by substituting the various values for the in place of n, we have to go with, then by substituting 0 you can have this is 1 plus 2 z inverse plus then you can have that is about the 2 square z power of minus 2 and 2 cube into z power of minus 3 and so on. We can have like this. Now I can go with 3 into multiply with the z now. This is z inverse, so that z inverse plus 2 into z power of minus 2 plus 4 into z power of minus 3 plus 8 into z power of minus 4, etc. we can get now. So now we can write this is in the sigma form. 3 is obviously outside, so that sigma n is equals to here minus 1 onwards, so that I can write n is equals to 1 to infinity, because up to infinity it is having. Here a term is what, here the some 2 power of n term is 0, 2 power of n term is 0, so that I can write 2 power of n minus 1 into z to the power of minus n, z to the power of minus n, so that we can, this is in the form of what, it is in the form of standard z transform only, so that we can write this is 3 into sigma n is equals to 1 to infinity and 2 to the power of n minus 1 into this is n minus 1 onwards, from n is equals to 1 onwards, n is equals to 1 onwards, if you take the amplitude is 1 from the unit step signal, so that I can write this is u of n minus 1 into the z power of minus n. Now this is very similar to the standard formula of Z transform, so that I can write this one is as, this one is what, now this 3 remains same, and this part we can call it is x of n, and into the sigma n is equals to 1 to infinity, and this is x of n into z to the power of minus n, so that we can write this is 3 into you can write, now you can write this is about the 3 into sigma n is equals to 1 to infinity into 2 to the power of n minus 1 into u of n minus 1 into z to the power of minus n. Now this is x of n, so that what is x of n? You can write x of n is equals to 2 to the power of n minus 1 into u of n minus 1. This is this one. So now you can have this one is about the x of n. This is x of n. So similarly we have to calculate the Laplace of z in z transform of any given signal. By solving the one more question, I am going to close this inverse z transform. This is about the inverse z transform. Two more problems we have to discuss. One is what? One is, the first one is x of z is equals to 1 by 1 minus a into z to the power of minus 1. Then it is very similar. The first what we have, x of z is equals to 1 by 1 minus a into z inverse, whose ROC is also given, that is a region of convergence, modulus z greater than modulus a. This is the thing. Then I am going with the solution of this problem now. See this one. So now x of z is equals to we have 1 by 1 minus it is 1 minus a into z power of minus 1. So that from the Taylor's expansion you can go with this one is you can take this one is the numerator, this denominator will upside, so that you can have 1 plus a into z to the power of minus 1, a square into z to the power of minus 2 plus a cube into z to the power of minus 3. Like that we can have. Now this can be represented as what? It can be represented as sigma n is equals to 0 to infinity, that is a n into z to the power of minus n. So then we can expand this by making use of the unit step signal. Sigma n is equals to 0 to infinity a to the power of n into u of n into z to the power of minus n. So that x of n, what we have now, x of n is equals to a to the power of n into x of n. This is nothing but it is a x of n. This is the x of n. If we apply this z transform on this x of n, then the resultant z domain signal x of z will be 1 by 1 minus a into z power of minus 1. So now here also you can get the one more problem, that is, see this one. Here we have the question, that is x of z is equals to 1 by 1 minus a into z power of minus 1. But here ROC is mentioned what? Modulus z is less than modulus a. So that I can write this equation in another form, that is about x of z is equals to, I can write 1 by minus a into z power of minus 1 plus 1. By using the Taylor's expansion method, I can write x of z is equals to 1 by minus a into z power of minus 1 plus 1, and I can write this is about, that is minus a to the power of minus 1 into z plus, minus, then minus a power of minus 2 into z power of 2 plus minus, again minus, a power of minus 3 into z power of 3, like that we can have. So that it can be written minus as it is, so that sigma n is equals to minus infinity to 0. It is going with the minus infinity to 0, that is a power of minus 1 whole to the power of n into z to the power of minus 1 whole to the power of minus n, you can write, because it is plus. So that I can write minus sigma n is equals to minus 1 to infinity a to the power of minus n into z to the power of n, minus into minus plus. So that this is, again I can write sigma n is equals to minus 1 to infinity. I can write this is about a to the power of minus n into, this can be written as u of n minus 1. It is a time reversal operation. So that z to the power of then minus n, minus 1 of minus n, such that now this will be in the standard form only. So that x of n is equals to, we can write minus a to the power of minus n into u of minus n minus 1. This is about what? It is the inverse z transform of the given signal. So in similar way we have to solve the many problems in the inverse z transform, and whatever I shared the material, in that material I have solved the many problems based on the same concept. You have to solve the remaining all the problems. Due to the time constraint, I am not going to solve the each and every problem which is solved in the shared material. So that watch the video completely and go to the material and practice every problem, such that you will be good at the Z transform. Then the next class I am going to discuss. In the next class I am going to discuss about the fourth unit, that is about the discrete time signals and systems. Anyway, discrete time signals and system, 50% of that unit we have already discussed in the first unit itself, because the first unit is about the introduction to the signals and the system, in which we have studied the various classifications of the signals and the classifications of the system, in which we have studied the continuous time signals and the discrete time signals. The discrete time signals actually that are mentioned in the fourth unit, but we have discussed that is in the first unit itself. And one more thing we have to discuss, that is in the fourth unit, that is the discrete time systems. We have already studied discrete time systems in the first unit itself, because in the first unit we have studied the various types of systems, in which we have studied the continuous time system, discrete time system, the analog system, digital system, causal system, non-causal system, time invariant, time variant, linear, non-linear system. All these systems we have studied in the first unit. So that we left with the 50% of fourth unit. That 50% of fourth unit, tomorrow in the tomorrow's class I am going to cover that one, and with the 2-3 classes this total syllabus of the signals and system is going to completed successfully. So that students, don't waste the time, try to write the notes from the shared videos, and not only for the signals and system, for all the subject, try to prepare the good notes, such that your preparation will be very simple, because exams are approaching very soon. Most probably you will be having the external theory exams in the month of September, in the last week of September. So that be cautious about the examinations and be prepared for the examinations, such that you can score the good marks, because question paper itself, it is offering the more options, such that you can score good marks in the examinations. So students, my request is that don't waste the time, and try to prepare the notes from the shared videos, and as per my signals and system concern, practice the more problems in the from the shared videos, such that you will be good at each and every topic of the signals and system. Thank you, students.